Curiosity Corner, your go to source for AI concepts. Whether you're an expert in the field or just starting out, our goal is to provide you with high quality and engaging content that will expand your knowledge and ignite your curiosity. Hi, I'm Rishika, and I'm excited to be your guide on this journey. Together, we'll explore support vector machines in machine learning. We'll cover everything you need to know from the fundamental concepts to the practical applications. Whether you're a student, a professional, or just curious about the world around you, there's something for everyone. So get ready to dive in as we explore SVM like never before. With our engaging content, expert insights, and interactive approach, you're sure to come away with a deeper understanding and a renewed sense of excitement for the world of SVM. So hit that subscribe button and turn on notifications so you don't miss out on any of our upcoming videos. Let's learn together and make a difference in the world. Introduction. Welcome to the Unveiling the Power of the Support Vector Machine presentation. In this presentation, we will explore the SVM algorithm and its implementation in Python. We will cover the key concepts, advantages, and applications of SVM. Let's dive in. What is a support vector machine? A support vector machine is a popular supervised machine learning algorithm used for classification and regression tasks. It's particularly effective in cases where the data is not linearly separable. The SVM creates a hyperplane or decision boundary that separates the data points into two different classes. The goal of an SVM is to find the optimal hyperplane that maximizes the margin, which is the distance between the hyperplane and the closest data points to each class. The data points closest to hyperplane are called support vectors, hence the name support vector machines. SVM can handle both linear and nonlinear classification problems by using a technique called the kernel trick. The kernel trick allows SVM to transform the input space into a higher dimensional feature space, where the data becomes separable by a hyperplane. During training, the SVM learns the best hyperplane based on the training data. Once trained, it can classify new, unseen data points by determining which side of the hyperplane they belong to. SVMs have proven to be effective in various domains, including text classification, image recognition, and bioinformatics. They are known for their ability to handle high dimensional data and their robustness against overfitting. Key concepts of SVM. To understand SVM, we need to grasp key concepts such as hyperplanes, support vectors, margin, and kernel functions. Hyperplanes are decision boundaries, support vectors are data points near the decision boundary. Margin is the distance between the hyperplane, and support vectors and kernel functions allow SVM to handle non-linearly separable data. Advantages of SVM. So, SVMs offer several advantages that make them a popular choice in machine learning. First being effective in high dimensional spaces. SVMs perform well even in datasets with a large number of features such as text classification or image recognition tasks. Versatility. SVMs can handle both linear and nonlinear classification task functions. Robustness against overfitting. SVMs aim to maximize the margin between classes, which helps in generalizing well to unseen data. Effective and limited samples. SVMs can handle datasets with a small number of samples because they only rely on a subset of training data. The support vectors to create the decision boundary. Handles outliers well. SVMs are less affected by outliers in the training data. Mathematically well founded. SVMs are based on solid mathematical principles and have a very strong theoretical foundations. These advantages make SVMs a versatile and powerful tool for various classification tasks. However, it's worth noting that SVMs may have some limitations such as sensitivity to the choice of hyperparameters and slower training times for larger datasets. Implementation of SVM in Python. Implementing SVM in Python is relatively straightforward, using popular machine learning libraries such as scikit-learn. Here's a simple example on how we can implement SVM for a binary classification problem. In this example, you start by importing the necessary libraries, then you prepare your data where X represents the input features and Y represents the corresponding labels. Next, you split the data into training and testing sets using the train test split function from scikit-learn. After that, you create an SVM classifier by instantiating the svm.svc class. The kernel is equal to linear parameter specifies that a linear kernel should be used. Then you train the classifier using the fit method, passing the training data in bracket xtrain and ytrain. Once trained, you can use the train classifier to make predictions on the test data using the predict method. The predicted labels are stored in y_pred. Finally, you evaluate the accuracy of the classifier by comparing the predicted labels and with the true labels using the accuracy score. Remember to replace the prepared data function with your own data preprocessing steps, ensuring that your input features and labels are in the appropriate format for SVM training and prediction. Conclusion. In this presentation, we have comprehensively explored the power of support vector machines and its implementation in Python. SVM offers excellent performance, handling high-dimensional and non-linearly separable data. Its versatility and widespread use in various domains make it a valuable tool in the machine learning toolkit. Start leveraging the power of SVM in your projects today. Thank you.